We'll check that. Pretty sure it's Monday. There it is right there, next Monday. Okay, I'll try and finish 6-7 today if we can, and then we'll have a couple days to review. Should be in good shape, but we'll see. Okay, so it says graph and label as growth or decay. So I want you to go ahead and graph each one of these. So this is one that you've got to be familiar with. Don't be surprised if there's a problem on the test that just says graph the exponential function with a base of e and label the points. Again, it's got horizontal asymptote, it's got a y-intercept and that sort of thing. Okay, it goes through the point. Let's see, those points are -1, 0, and 1. And it goes through, well, this one's easy. If it's an exponential and we haven't moved it left, right, up, down, or anything like that, goes through 0, 1. The negative means reciprocal, so that's going to be 1 over e, and this is going to be 1 comma e. So it's going to go through these points right here. 0, 1, 1 comma e, and we'll just eyeball that. Remember, e is about 2.7. And then this would be 1 over e, or that would be about 1/3, somewhere in that neighborhood, so we'd be about right there. So the graph's going to look something like this. It's going to come out here, run along the x-axis. It's got a horizontal asymptote of y equals 0. And we labeled those 3 points right there. Okay, they're these guys. Okay, is this growing or decaying? Is this getting bigger or getting smaller? Okay, so this is exponential. This one's growth. Okay. What does the negative with the x do to this graph? Okay. Whenever you multiply by a negative, it's a flip of some type. Okay, it's a horizontal flip. It's a flip across the y-axis. Okay, it's a little weird. If we flip it horizontally, okay, we flip everything across the y-axis, change everything on the right for the left and left for the right. So this point, instead of being 1 comma e, it's going to be -1 comma e. So -1 comma e for that point right there. This point is on the y-axis, so it doesn't go anywhere. That's going to be the point 0 comma 1. And then this point that was at -1 comma 1 over e is going to be at 1 comma 1 over e. And the graph's going to look something like this. Okay, it's got a horizontal asymptote on the left side here. It's got a horizontal asymptote of y equals 0 on the right side here. And there's our graph. Growth or decay? Okay, decay. Okay, because instead of growing, this is getting smaller and smaller and smaller. The values are decaying, if you want to think of it that way. Okay, any questions there? Okay, good reminder of a very easy transformation and a very good reminder of how to graph an exponential function. Remember, those are the key points on an exponential function. You'd want to know how to graph those. Okay, so there are lots of quantities that increase or decrease exponentially, and we're going to go through a formula that we can use to solve these types of problems. Okay, this is called the Law of Exponential Change. That's it right there. Okay, we want to point out what each of these pieces are. Okay, this right here, this is called the initial amount. Okay, and the way we say that is we say A naught. Okay, that little subscript there, that little 0 down below, okay, we read that as A naught. That's the initial amount, or the amount at time 0. That's why the 0's there. Okay? And that K right there is the growth or decay constant. And we just typically use a C for that. I suppose a K for that. I suppose we could have used a C, okay, for constant. But that's what it is. It's the growth or decay constant, okay? It's also sometimes called the growth or decay rate. So many times it's a decimal. Okay, so be looking for that. It's kind of like the rate. kind of like the interest rate. Okay, and it's going to be exponential growth if k is positive. So the exponent is positive right here. If this is a positive number, kind of like this one was up here, we're going to have growth. And it's going to be exponential decay if k is negative. Okay. All right. So the cool thing about this section is if you already did the stuff in 6.6, if you started those, if our discussion about interest rates, doubling time and different things like that, present value, if those arguments made sense, if that was kind of, okay, I can see how these formulas work, then this section is going to be pretty easy because this actually is very much like A equals PE to the RT. Okay, it's kind of like continuous compound interest or continuous growth or continuous decay. So it's going to be very similar to that, and the way we're going to talk about them are the same. And the cool thing about this is as you go through and do the problems, if you look at it real carefully, some of these, they already give you the equation. Okay? Everything's all set up. All you have to do is know what to put where and what each part of the problem is. So it says a culture of cells obeys the law of uninhibited growth. So what that means is if you've got a petri dish or you've got, say, an unlimited petri dish, and you put some bacteria in there, some cells in there, and you want them to grow, okay? If we let them just grow and give them plenty of food and water and all that sort of stuff, they'll just grow exponentially, okay? There's nothing to inhibit their growth, okay? So that's why we call it the law of uninhibited growth, okay? The formula that describes the growth of these particular cells is right here, okay? So we're giving you the formula. The amount is going to be equal to 75 and then times e to the 0.25 times t, where A is the number of cells and T is the time in hours. So A is going to be the amount of cells and T is the time in hours. Yeah.
What is 75 and 0.25?
That's what we're going to figure out right now. Okay. So it says, what is the initial number of cells? Okay. In other words, how many cells are there when time is 0? Okay. Right at the beginning. Okay. Right when we click our stopwatch, we plunk this little cell down in this petri dish. We start our stopwatch. It starts off at 0. So how many cells are there initially? Well, there are a couple ways to figure this out. You'll notice that this little formula right here, okay, this law of exponential change, we said that is the initial amount. That number in front of the exponential function, that is the initial amount. Well, let's check and see. So you'd guess that the answer is 75. Let's just check and make sure. What is the amount at time 0? So this would be 75 e to the 0.25 times 0. 0.25 times 0 is 0. E to the 0 is 1. And 1 times 75 is 75. So the answer is 75 cells. Okay, what is the growth rate? What is the growth rate? Okay, that number right there, that decimal usually, in front of the t that's up in the exponent, that is like the interest rate for these cells. Okay, so that's all it's asking for is what is this number that goes in that place right there? What's the coefficient in front of the t? And the answer is 0.25. Okay, so we'd say 0.25. Okay, if we translated that into an interest rate, that would be like, 25%. Per what? Per hour in this case. These are growing pretty darn fast. It would be really cool if we could find an interest rate in an account with money at a bank that would pay 25% per hour. Okay, but that is the growth rate. Okay, now we normally don't change that into a percent. We just leave it like that, but you could think of it as a percent if you need to. And then it says how many cells are present after 10 hours. So we plop down 75 of them at time 0, just to begin. We put 75 in this petri dish, and then we let how much time go by? 10 hours. Getting a quarter more every single hour. It's probably going to grow pretty quickly. How do we find the answer to this problem? Plug it in. Okay, yeah, we just plug in. They're telling us 10, they're asking us to find A. So A of 10 basically is what we're finding here. And it's going to be 75 e to the 0.25 times 10. So we'll grab a calculator and we'll plug that in and see what we get. So this is 75 and then e to the 0.25 times 10, we'll close the parentheses, 913.68. Okay, now because we can't have a, 6/10, 7/10 of a cell, okay, we're just going to say that this is approximately, what did I say, 900 what? 913. Okay, so this is 913 cells. Okay, next question. If there are 5,956 cells present, how many hours have passed? Okay, what does this have to do with question C? Is it like question C? It's the opposite, right? In question C, they gave us the time they wanted us to find out how many cells there were. Now they're telling us how many cells there were. They are asking us to figure out how much time has passed. So they're telling us that we have 5,956 cells. There were 75 to begin with. Our growth rate is 0.25. They're asking us to find T. Okay, what do we do to solve this equation right here? Yep, divide by 75. So this is going to give us, well, let's see, does that have a nice answer? 5976? 56 divided by 75? I'm guessing not. Okay, it's that ugly number right there. I'm going to just leave it as this ugly number right here. So this is going to be 5956 divided by 75 equals e to the 0.25 t. Now, I've got that variable t up in the exponent where I can't work with it. What tool allows me to bring that down? An ln. So I want to undo the exponential base e, or I at least want to use that property of logarithms. So I'm going to take the ln of both sides. This is going to be the ln of 5956 divided by 75 equals 0.25 times t. So how do I get the final answer here? Divide by 0.25. So I'm going to have t equals the ln of 5956 divided by 75, and then we're going to divide that by 0.25. So we'll grab the calculator and we'll throw that in. So this is ln 5956 divided by 75, that calculation I did previously, okay? And then we're going to divide that by 0.25. Please make sure you close the parentheses, because we're taking the ln of this little fraction right here, 5956 divided by 75, not the ln of the whole thing. We're not dividing by 75, then dividing by 25, then taking the ln. So make sure you use parentheses the right way. Oh, 0.25. Very good. That's going to be much better because what does that mean? Yeah, 17.49 hours, or about 17 and a half hours. So we're going to say 17.5 hours. So think about that for just a second. We put 75 in there to begin with, and not even a day later, okay, in 17 and a half hours, there are almost 6,000 of them. Gone from 75 up to 6,000 that quickly. Okay? Any questions? Okay. All right, next problem, example 2. It has some things to do with example 1. Let's see if we can pick these up. Okay, it says a colony of bacteria obeys the law of uninhibited growth. So it obeys this law of exponential change, and the fact that its growth means that that K is positive. That's it. That's all that means. So we're going to use this formula, and we know K is going to be positive. Okay? It says there are 5 bacteria present initially, and the colony doubles in size after 4 hours. Then answer those questions. Find the growth rate. How many cells are present after 17 hours? How many cells are present after 1 day? And how long does it take the population to triple in size? Okay, what's the difference between example 1 and example 2? Yeah, okay, Chase has got it right. They didn't give you the formula. This one's pretty easy. There's the formula right there. Okay? All we have to do is pick out, oh, that's the initial amount. That's the growth rate. Oh, they tell us what t is, we can find a. Or if they tell us what a is, we can find t. On this problem, we have to come up with the exact formula. Okay, now, it does help us out a little bit. It does say there are 5 bacteria present initially. So if the formula is a equals a naught e to the kt, they did give us, what's the 5? It's the initial amount. It's the a naught. So here's the formula we're working with so far. It's going to be 5 e to the k times t. Now, in order to be able to do this problem, compare this with what they gave us in example 1. They gave us 75 and they gave us 0.25. They gave us the k. They gave us the growth rate. They didn't give us that here, so we have to find k first. In fact, look at part A. It says find the growth rate k. So let's go ahead and go through and find that. How are we going to do that, though? Take a good look at it. Take a look at the information they gave us. Think about the stuff that we dealt with in the last section when we were talking about money. Emily?
Does it make the first, that a that's on the other side of the equal a
Exactly. They said it doubles after 4 hours. So they told us a time, and in code they told us an amount. So on this problem, we get 10 cells after 4 hours. So if you take a look here, there's only one variable in here. There's only a k missing. So we can solve this. We're going to divide this side by 5, divide that by 5. Now this should look familiar. What do we get over here when we take 10 and divide it by 5? We get a 2. 2 equals e to the 4k. Now why is that 2 there? Because it doubled in size. Okay, remember when we were finding the doubling time for an interest or a particular interest or something like that? Okay, we're going to finish solving this by taking the ln of both sides. So this is going to be the ln of 2 equals 4k. So that means k is going to be equal to the ln of 2 divided by 4. So let's grab our calculator and let's figure this out. ln of 2, got to close the parentheses there, and we're going to divide that by 4. Okay, there's our answer. Now, if you round too much, your answers are going to get quite inaccurate very quickly. So we're going to say k is equal to 0.17, and let's go 6 places, and then I'm going to show you something else. 173286. Okay, there's k. Okay, what that means is our formula on this problem is going to be this. A equals 5 was the initial amount, and then it's going to be e to the 0.173286 times t. So does this particular bacteria grow faster or slower than the last one?
Slower.
A little slower. Okay. This one's 17% per hour. The other one was 25% per hour. Okay, now, okay, I think I showed you how to store variables earlier this year, right? Okay, rather than write these 6 decimals or all 10 of these down over and over and over again, let's be as accurate as we can, but let's make it easy on ourselves. Let's store this. So we hit the store button right here. Let's store that in k. So I'm going to hit store, and then I'm going to hit alpha, and the k is above the 8. It's the open parentheses. So we're going to store that in k. So whenever I type a k in, it's going to grab that little ugly number, 0.7 or 0.173286, blah, 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 and it's going to use that value for us. Okay, any questions? Okay, how many cells are present after 17 hours? What do we need to do here? Plug in 17. We're finding a of 17. So if you plug in a 17, let's go ahead and figure out what that is. So the formula is 5 e to the k. Thank you very much. So I'm going to hit alpha k, and then we're going to times that by 17 hours. 5 e to the k times 17. 95. So we end up with 95 cells. Next question. How many after 1 day? We plug in 1. We plug in 24, because remember, time is measured in hours here, so if they give us this measurement in days, we're going to convert that. So I'm just going to recall that last command, and we're going to type in 24 for the hours rather than 17 for the hours. Hit enter, and that means there are 320 cells. So it started with fewer, and it's growing at a slower rate, so there's only 320 cells there. And then it says, how long does it take the population to triple in size? I don't want anybody to say anything out loud. We did a problem very much like this just yesterday. So I want you to go ahead and try and solve that problem. How long does it take it to triple in size? And even if you just read the problem and think about it, you can probably take a guess at what a reasonable answer would be. You won't know exactly what it is, but you could maybe say, well, gosh, it's got to be somewhere in this ballpark. What do I change in this formula right here if I want it to triple in size? Change the A to 15. 15. 15 equals 5e to the 0.173286 times t. Because that would be triple in size, right? Now, if you wanted to put a p here, you could put a 3p there. Okay, now either way, we are going to end up with a 3, just like when it doubles, we end up with a 2. So when I divide by 5 on both sides, I end up with 3 equals e to the 0.173286 times t. I'm going to take the ln of both sides. So the ln of 3 on this side equals 0.173286 times t. And then how do I get the t by itself? Divide by that ugly number right there. So that means t equals, well, let's grab our calculator and let's figure this out. That's going to be the ln of 3, and we're going to divide it by, we could type that in or we could just grab k, 6.3. Now, can somebody tell me, so we're going to put 6.339 hours. Can somebody tell me why that's a reasonable answer? Josh. The colony doubles in 4 hours, so to triple it's going to be a little bit more than 4. Okay? Would it be more than 8? No, because if it doubles every 4 hours, it would double in 4 hours, it would quadruple, it would double again in 8 hours. Does that make sense? So it would have to be somewhere in between. Okay, around 6 would be a decent guess. Now it's not exactly 6. It doesn't work in kind of a linear fashion like that at 6.339. Okay, but it's got to be somewhere in between 4 and 8. That would be a reasonable guess. Okay, any questions there? Okay, all right, let's take a look at the next problem then. Let's see. The size p of a population of rabbits at any time t in days obeys that function right there. Chase, what's nice about that? Gives us the whole function, right? We know what function we're dealing with. After how many days will the population reach 1,000 and then 2,000? So we're going to take this right here, and where are we going to put it? We're going to put it right there in the p. So this is going to be 1,000 equals 500 e to the 0.02 times t. Now, that's a fancy way, or actually that's a really simple way of asking us what is the doubling time. Okay? Because we're going to go from 500 to 1,000. How long does it take this population to double, right? Okay. So this is a population of rabbits, right? Anybody raised rabbits? Okay. You have a rabbit, okay? So rabbits breed pretty quickly, right? Okay, they can reproduce, okay, after just a couple of months. Okay, you can have lots of rabbits really quickly. Okay, what's the growth rate in like as a percent? 2% per, what's time measured in? In days, 2% per day. Okay, so you get 2% of a rabbit per day. All right, it takes quite a few days to make a rabbit, but let's see what happens here. Okay, so we're going to figure this out. How long does it take to double in size? Now, if you had to take a guess at this, anybody want to take a guess? I taught you a way where you could guess how long it would take it to double based on the growth rate or the interest rate. What'd you get? 72 divided by 2 would be about 36. Okay, so we're going to take the ln of 2. It's going to equal 0.02 times t, and then we're going to divide by 0.02. So we get ln 2 divided by 0.02, 34.65 days. Okay. Okay, if this was a fancy way of asking how long it takes to double in time, this would be a fancy way of how long it takes to quadruple in time. Now, whenever we do a doubling time, this ends up being 2, right? Quadruple, what's this going to end up being? It's going to end up being a 4. So we're going to have 4 equals e to the 0.02 times t. Now, just for the heck of it, I'm going to put 2,000 here. 500 e to the 0.02 t. If I divide both sides by 500, 2,000 divided by 500 is 4. So this is going to be the ln of 4 equals 0.02 t. We're going to divide by 0.02. So same calculation we did before, it's just we're going to have ln 4 rather than ln 2. So I'll just recall that. Type in a 4, hit enter. It's going to take 69.31 days. And it'll quadruple. Okay? Any questions? Okay, you sure? Okay, let's move on to a different type of problem. These problems, you have several on your assignment. They're called radioactive decay and half-life problems. Okay, so radioactive substances don't behave like normal things. Like if you leave a piece of wood out, okay, I mean, it just kind of rots and then pretty much it starts to just disappear, okay? Radioactive substances behave a little bit differently, okay? They behave according to the same type of exponential growth and decay formula that we were working with earlier, okay? Only it kind of does it in a weird way, okay? So, let's talk about what half-life is. Half-life is the period of time required to a substance to decay to half of its original amount. Okay, and because radioactive substances typically last a long time, we talk about them in terms of their half-life, how long it takes for half of them to decay away. So let's take a look at example 4. This is one that we can probably figure out without using a calculator, at least for the most part. Say we have 80 pounds of a radioactive substance with a half-life of 3 years. So we start out with 80 pounds. We let 3 years go by. Shane, how many pounds would be left after 3 years?
After 3 years, we would have
Start with 80 pounds. Half of it's going to decay every 3 years. Its half-life is 3 years. What'd you say? 40, right? Exactly half. We let one half-life go by. We let the equivalent of time that takes half of it to decay away. So half of it would be gone. So we'd be left with 40 pounds. Okay, now, if you let 3 years go by and 40 pounds disappear, you would think that if you let another 3 years go by, another 40 pounds would disappear, right? Not the case. That's not the way it works. It decays according to how much is left. If you let a half-life go by, half of it disappears. So if we let another 3 years go by, so now we're 6 years gone by in total, half of what was there at 3 years is gone, so how much is left now? 20 pounds. Let another 3 years or another half-life go by, and half of that would disappear, so we're going to be down to 10 pounds. Let another half-life go by, another 3 years goes by, we're down to 5 pounds. And after 15 years, we're down to 2.5 pounds. Okay? So it's a little weird the way that works. First 3 years, 40 pounds is gone. We let another, well, let's see, we got to 15. We let another 12 years go by, and only 37.5 pounds disappears. Okay? Yeah.
Isn't this a paradox because you can never reach zero?
Well, it's not a paradox.
Well, I heard something.
Will it ever reach zero? Well, when the last nuclear molecule, when it decays, it'll be gone. Okay? So mathematically, it works right up till the very last instant. Okay? All right. Everybody good there? Okay. All right. So let's take a look at a problem. Okay, there are lots of radioactive substances. Some of them are harmful, some of them are not. Most are not. Okay, they're so mildly radioactive it wouldn't affect us. So if we take a look at iodine 131, okay, it's radioactive and it decays according to the exponential function right there. Okay. Chase, what's nice about this? Okay, there's a function. Okay. They give us the decay rate. Okay, notice that this is the first one we've come across where the decay rate is negative. Okay, the exponent has a negative in it. Okay, and it says A naught is the initial amount and T is the time in days. And then it says, what is the half-life of iodine 131? So it tells us the decay rate, but it doesn't tell us what the half-life is. Those two things are always going to go hand in hand. If you have one, you can figure out the other one. Okay? Well, we have the decay rate. It says, what is the half-life? How long does it take for half of this stuff to decay away? Okay, now Chase, what's not so nice about this one right here? I'm pointing to it. Okay, they didn't give us the initial amount. Now, as far as figuring out what the half-life is, does that matter? No, just like it didn't matter if we wanted to figure out the doubling time for an amount of money. Okay, for a particular interest rate. Okay, we can use whatever A naught we want. So if I have A naught right here, and it's e to the negative 0.0871 times t, how do I represent half of that? Yeah, we can do 0.5 A naught. Now, if you're not comfortable with that, you could just pick an amount. We could say, hey, let's start off with 100 pounds. What would half of 100 be? 50. So you put a 50 here. Now, regardless of the way you solve either one of these, or what you start with, when you begin solving this, 50 divided by 100 is 0.5. 0.5 A naught divided by A naught is 0.5. And then over on this side, the A naught would cancel, the hundreds would cancel, and we'd have e to the negative 0.0871 times t. So, if they tell us the decay rate, we can find the half-life because we can now find the time that's required for it to decay to half. Now, I actually like writing this as a 1/2 equals e to the negative 0.0871 times t, because the 1/2 there just kind of is a visual reminder, this is half-life. Remember what happened when we quadrupled? That was a 4. Remember what happened when we doubled? That was a 2. If we tripled, it was a 3. If we want the half-life, we just make it a half and solve for what t is. Got it? Okay, so how are we going to finish this? ln. So ln of 1/2 equals negative 0.0871 times t, and then we're just going to divide. So we get t equals So ln 0.5 divided by negative 0.0871. Now, we're taking the ln and dividing it by a negative. Are we going to get a negative answer? Nope. Because the ln of a fraction between 0 and 1, the ln of a decimal between 0 and 1, think about the way the graph looks. All these answers here are negative. We're finding the ln of 0.5. It's going to be a negative. So this is going to be a negative divided by a negative. That's going to produce a positive. I'm going to hit enter. The answer here is 7.958 what? Okay. It is days. Okay. 7.958, is that what it was? Days. That is the half-life. You let that much time go by. You let 8 days go by, basically, and half of it will decay away. Yeah.
So, where did you get the A naught on the left side? 0.5 A naught.
This right here?
No, on the.
That right there.
Yeah, that is.
Well, we said if you start with the initial amount and we let a half-life go by, we'd have half of it left. 0.5 times A naught. Okay? If you want to use 100, we'd say, well, what's half of 100? So we put 50. Everybody good there? Anything else? Okay. How long does it take 100 grams of iodine 131 to decay to 20 grams? What's that?
A little over 2 days.
A little over 2 days. Well, let's see. We start off with 100. How long would it take to get to 50? It would take a half-life. It would take about 8 days. Okay, so then we've got to get to half again would be 25. 16 days would put us at 25. So how long do you think it would take to get to 20? 8 days roughly is a half-life. So 8 days is half. Another 8 days, 16 days would be half again. Another 8 days, 24 would be another half of that. So that would be even less. So somewhere between 16 and 24. Does that make sense? Does the logic make sense? Okay. So in order to figure this out, what they've given us right here, what is that 100? That's A naught. That's the initial amount. So in this problem, we can now say, you know what? They told us how much we start with. We start off with 100 grams. And how much do we end up with? We end up with 20 grams. The only variable in the problem at this point is T, which is what they said. How long does it take? So let's finish solving this. Whoops, divide by 100. Cancel those off. E to the negative 0.0871 times T. Let's see, this would be, cancel the zeros, 2 and the 10. This would be 1/5. Okay? It's a good thing they don't keep track of 1/5 time like they do half-life. Okay? This would be like the 1/5 life. Okay, that would be a little bit silly. Okay? So this is going to be the ln of 1/5 equals negative 0.0871 times T. So we just divide by that. And remember, we're taking the ln of a fraction between 0 and 1, so that is going to be negative. So I'll just recall that. 1/5 is 0.2. Hit enter, it spits out the answer. We're expecting something between, what did we say? Something between 16 and 24. Let's see if we're right. 18.47. Okay? So the answer to this one is 18.47 days. Okay? That's how long it's going to take to decay to 20 grams. Okay. And then we're going to finish this with this problem, and we'll finish up the section tomorrow. Carbon-14 is really important. Can anybody tell me why carbon-14 is important? It is everywhere. It's in every living thing. Okay? Trees, plants, spiders, bugs, crustaceans, human beings. Everything that's living has carbon-14 in it. Okay, carbon-14 is just mildly radioactive. It's not harmful or anything like that. Okay, because every living thing has carbon-14 in it, and it's very stable and it has a very long half-life. They use carbon-14 to do what?
They like really
Date really old things. Okay? So if they dig up some, handle for a tool and it was made of pine or something like that, they know how much carbon-14 is present in a sample of pine initially. They can figure out how much carbon-14 is left, and they can figure out how much time went by. Does that make sense? Okay. So it says carbon-14 is a radioactive substance that decays according to this function right here. Okay? So the law of exponential change. If the half-life of carbon-14 is 5,600 years, now this book uses 5,600 years. It's a little bit different than that. They just rounded it. Okay? It's 56 years. Find K. So define the decay rate. So we let 5,600 years go by, and half of it will disappear. So if you start with A naught, and you let 5,600 years go by, how much will be left? Half of A naught. Okay. Now everybody look at that. Everybody good there? Isn't this just exactly the same as part A of problem 5? Same thing. If you're more comfortable picking a number for this, go right ahead. It doesn't make any difference because you're going to divide by whatever that number is, or whatever A naught is. Those are going to cancel, and you're going to end up with this. 1/2 equals e to the 5,600 times k. So to finish this off, we take the ln. Just like we did before, it's going to be the ln of 1/2. This is going to be 5,600k. And we're going to end up with k equals, so we'll type this into the calculator. Oops, ln 0.5. And then this is going to be 5,600 years. Okay. This is in, what does that e to the negative 4 mean? Okay, it's that's scientific notation, basically. Okay, it's saying we're going to have a negative answer. We're going to take this decimal, and because it's a negative 4, we're going to move it 4 places to the left. So the answer is, so if we've got 1.23, what was it? 77. We're going to move it this way, 4 places. So there's 1, 2, 3, 4. Put the decimal right there. So there's our answer, negative 0.000123777. That's what k is. And once we have k, we've got probably the most important part of the formula. We know the decay rate for carbon-14, and that way we can date things based on how much we know should be there versus how much is there. Okay, have a great day. We'll finish this up tomorrow. Get started on the assignment. Please have 6-6 done.